Assalamu alaikum everyone. My friend Ekramul Al-Amin, ID 2005022, and I, Farhad Al-Amin, ID 2005042, will be presenting you the theme and core mechanism of SSR, screen space reflection. I'll be covering the first part of our presentation. So, what exactly is screen space reflection? In simple words, it's a clever trick used in computer graphics, especially in video games, to create realistic reflections very quickly. The main idea is right there in the name screen space. It means we only use what is currently visible on your screen to create a reflection. Look at the diagram. We have a reflective surface, and instead of doing some heavy complicated 3D math, the system just looks at the pixels already on the screen and reuses them to draw the reflection. This makes it super fast and dynamic, which is perfect for games where things are always moving. So, now to understand why SSR is so cool, let's quickly look at the old ways of doing reflections. First, we have environment maps. Think of this like a wallpaper. You take a 360-degree photo of a room and wrap it around an object. It's fast, but it's static. It doesn't change. So if your game character walks past a shiny object, you won't see their reflection. Then there is planar reflections. There is more accurate, but it's very slow because it forces the computer to render the entire screen a second time just for the reflection. Plus, it only works perfectly flat surfaces like a mirror or camera. And finally, there is ray tracing. This is the most realistic method, but it's traditionally very slow and needs expensive powerful graphics cards for most real-time games. It's just not practical. So the old methods were either too slow or not dynamic enough. This is where SSR comes in as the solution. As you can see, the key innovation is to stop thinking in complex 3D space and instead work in the simple 2D space of your screen. It reuses the screen's data to create reflections that are fast and dynamic. So how does it work? It's simple 5-step process. First, grab all the necessary data from the current screen. Second, for any shiny pixel, it calculates the direction the reflection should come from. Next, it follows that reflection line, step by step, across the screen. This is called ray marching. When the line hits another object on the screen, it grabs the object's color. Finally, it blends that color onto shiny surface. And that's a reflection. Let's look at this step a bit more closely. Step 1 is getting the input data. SSR needs 3 key pieces of information from the frame that has just been rendered. The color buffer, which is simply the image you see on the screen. The depth buffer. Think of this as a map that tells the computer how far away every single pixel is from the camera. And the normal buffer. This one is a bit more technical. It's a map that tells us which direction every surface is facing, up, down, left, right, or at some angle. This is very important for calculating how light should bounce. Now for step 2, generating the ray. Once we have our data, we look at each pixel on our reflective surface using the normal and the view direction. We can calculate the reflection direction using the simple formula you see on the screen. You don't need to memorize the formula, just understand that for every point on a shiny surface, we're calculating the path the light would take to bounce off it and into our eyes. The diagram shows this perfectly. The view ray comes in, hits the surface, and the reflection ray bounces off at an equal angle. And finally, step 3 is ray marching. This is searching part. We now have the direction of our reflection ray. The computer then marches along this ray, taking small steps. At every single step, it performs what's called the depth check. It's simple comparison. It checks the depth of the ray against the depth of the scene stored in the depth buffer. If the ray's depth is suddenly greater than the scene's buffer, it means our ray just gone behind an object that's visible on the screen, and that's a hit. The moment we get a hit, the search is over. The algorithm takes the color of the pixel we just hit, and that becomes the color of our reflection. So, Now to explain the algorithm in more detail and discuss its limitations and applications, my friend Ekramul will continue from this point onward.
Now let's continue our presentation. I am Ekramul Al-Amin, ID 200502. A fast walkthrough of the core shader loop. One glance will show where the time really goes. Only pixel flagged as reflective runs this shader. We capture the reflection direction with the classic physics formula. Heat color starts black, so a miss blends in nothing and avoid artifacts. Max steps sets quality. 32 is common, doubling it costs about 1 millisecond at 1080p. Step size grows with depth, so far away rays of farther and waste pure sample. We multiply by the projection matrix to stay entirely in 2D screen space. If the ray exits the viewport, we break early, saving up to 20% of iterations. A single cast depth read is almost free on modern GPU. If the ray's depth is greater than scene depth, we have hit geometry. No triangle math needed. Once we refresh that pixel's color, we stop marching. That keeps SSR under 2 milliseconds in Unity or Unreal. Finally, we mix the surface color with the reflection by material gloss, about 0.8 for wet puddle, zero point 0.2 for brushed metal. Now here are the knobs we can tweak to balance image quality against frame time. Max steps. Unity and Unreal default to 30. More steps hide gaps but cost about a millisecond at 1080p. Step size. Larger steps move faster but can miss the geometry. Running at half resolution, almost half the cost, while softening detail just a bit. A roughness threshold skips very rough surface and saves up to 30%. Rule of thumb, keep the whole pass under 2 milliseconds or 10% of the frame budget. Of course, everything has trade-offs. This slide highlights the main limitation you will run into. SSR can only reflect what's on screen. Off-screen objects disappear. That means no skyboxes or hidden rooms in the mirror. At the viewport edges, reflections cut off or stretch. So many engines fade them. Complex foreground geometry can also block background reflections. Despite those limits, SSR shines in practice literally. So let's look at where it's used. In games, it handles puddles, wet asphalts, mirror, and shiny metals without a second render pass. In VR, it adds convincing metal and glass reflection provided we watch performance. For architectural walkthroughs, it previews marble floors and glass walls long before the final purchase. Looking ahead, here's where the technique is evolving and how researchers are explaining it. Hybrid pipelines now let SSR handle on-screen rays while hardware ray tracing deals off-screen gaps. Temporal and stochastic tricks, blue noise, jitter plus hierarchical depth reuse, history, and cut noises. Adaptive step size, early exits, and variable rate shading keep the cost low. Neural add-ons like Lightformer hallucinate missing detail for mobile class GPUs. Stereo consistent SSR shares data between eyes, preventing eye strain in head-mounted displays. To wrap up, let's distill the key takeaways from everything we have just covered. SSR is fast and dynamic because it reuses the current frame's data. It's limited to visible objects and can show edge artifacts. Smarter sampling, temporal reuse, ray tracing fallbacks, and neural feedings tame those flaws. With these upgrades, SSR remains real-time graphic workhorse for reflection. That concludes our presentation on real-time screen space reflection. Thank you for watching.